Clarifications corner. First of all, here's new leg, I guess, in case you haven't seen it. It's literally exactly the same. I just moved some things around, recolored some wires, and it's just prettier. But the important part of Clarifications corner is going to involve this little thing. So a couple of videos ago, I added a call instruction, as in a bespoke special hardware call instruction, which was implemented as a conditional call to begin with. And we added this pin to a cond, which basically means, okay, we are in fact calling. This is specifically a call and not just a jump. And this pin, if we take a look at it, what it does, it goes all the way here and it connects to the stack register to let it know that it needs to save the IAR as opposed to its input. And importantly, it also needs to activate the stack register in order for it to actually save something. And the way I do that is by wiring it straight down and just activating it normally. Now, I still think this is a good approach, but this is bugged. As Christopher pointed out, thank you very much for that correction. I think I would have spent a bunch of time trying to pin this down, figure it out. So yeah, the problem here is, while this does work correctly when I am calling, this part here is not protected against backpropagation. So when I am accessing the stack or when I'm writing to the stack normally, so when this green wire lights up, what's going to happen is the signal is going to go up and it's going to seem like I'm calling, even if I'm not. So I believe all I need to do, well, first of all, I believe this is broken already. Like if we run this is an old unchanged program. Yeah, see, it does absolutely nothing. It's just broken. I believe that has to do with this. And the fix to this is going to be very simple. All I need to do is I need to add a one-way pin here. So this way, when it's on, it can propagate down, but it will not backpropagate from a write to stack to a call. Let's check if that fixes this program. It does. Cool. I'm not gonna look at this one yet. And in fact, that marks the end of Clarifications corner, and I am going to proceed with Tower of Alloy. Finally. We need you to help clean up the basement. Specifically, we want you to move piles of radioactive disks from an old reactor. Just be sure not to put a bigger disk on top of a smaller disk, or the whole ship will blow up. Okay, looks like I'm moving them with a magnet. The first 4 inputs will give you the following in order. Disk number, the highest disk number. Source, which location? Okay, so 0 source. Destination, where to, and spare. Yeah, the spare spot, sure. Control the crane. Yeah, magnet, this is a magnet. We're gonna be magnetizing depleted uranium, which I'm pretty sure depleted uranium, and maybe even uranium, I don't know, enriched uranium, I'm pretty sure it's not particularly magnetic. Like, I think you even need special equipment to actually detect its magnetic field, but I have no idea how magnets work. Okay, play with the magnet manually by using the arrow keys to move and enter to toggle. Okay, no problem. Let's boom. Boom. Everyone died. Okay, so you're not protected from failure. Okay, that's interesting. Play with the magnet manually. Yeah. Okay. Aha, and we're actually given the algorithm that solves this problem. Well, even though this doesn't explain how it works. And I'm going to explain how it works first of all. Actually, let me pull up my whiteboard. Okay, so what we have in Tower of Hanoi, this is a very classic mathematical puzzle I made. Oh, actually, let's first look here. A very classical mathematical programming puzzle, which is a very classic example of recursive functions. I'm trying to construct it back. The real problem with this, the real difficulty here, is the fact that you cannot stack large disks on top of small disks, right? This means that you are kind of limited with where you can put stuff. So for example, once I move the 0, this 1 I cannot move anywhere, so I have to put it here. Now I move the 0 again. If I take a look at the 2, there's only one other place it can go. It can only go here, it cannot go there. And then the 0 again I move somewhere, and the 1 can only go again into one other place, and so on and so forth. This continues as long as you can handle it, until you can actually move the lowest disk. Now, the solution to this is fairly simple, and the proof that it is the only solution is also fairly simple. So let's take a look at this. Again, same thing, Tower of Hanoi. What I need to have is I need to... Well, the problem as it is stated in the game is a bit specific. I'm gonna slightly simplify it. I'm not gonna try to move from this peg to some particular peg. I'm gonna try to just free this peg. I'm gonna try to move this entire tower somewhere else. I want this tower either here or here, right? In order to do that, of course, I necessarily need to move the 4, right? If I don't move the 4, well, nothing happens. But in order to move the 4, I need 4 to be free, right? Now, in order for 4 to be free, I need this thing off. So that's the first thing I will do. Sorry, bring this back. That's the first thing I have to do. I have to take this off. Now that the 4 is free, I move the 4. And now that we have moved the 4, I can move everything on top of the 4, right? And this is, in fact, the only solution to this problem. There's no other way to do this, because every step, as I just explained, was necessary. I need to free the 4, which means I need to move this tower, then I need to move the 4, and then I need to move this tower on top of the 4. Now, of course, right here, I can just select the entire tower and I can move it together, but that's not allowed by the actual problem. And what you have to do is you have to move the smaller disks in order to move the tower. But we may notice that this is a very much a recursive problem. So in order to move a tower of size 4, what I need to do is I need to move the tower of size 3. Then I move the 4, and then again I move the tower of size 3. But when I say I need to move a tower of size 3, what I actually mean is I need to move a tower of size 2, move disk 3, move a tower of size 2, right? And this means moving a tower of size 3. So that very quickly boils down to an algorithm, and I believe that's what we are provided with by the abductor. Let's take a look. Yeah, see, so move means move a tower of a certain size. Disk number effectively means size. If the tower size is 0, so just one disk, if we're moving one disk, then we can just move it, right? Otherwise, what we do is we move the tower of size n-1 from source to spare, right? We have from source to destination. Spare is just disregard spare. We move a smaller tower from source to spare, so that's exactly here. That's exactly this thing. Move it to spare. This is going to be my spare disk, my spare peg. Then move the disk from source to destination, and then again move the same tower, except this time we move it from spare, so from where it was to where it needs to be. right? This is completely trivial. This is a very classic example of recursion, and I think I should be able to implement it without any issues. Let me just import LML real quick. Okay, leg.lml imported. Let's call this recursion.lml, and let's see what needs to be done. Let's pretend like we know nothing. Trust me, that's gonna be temporary. But for now, let's pretend we know nothing, and let's just implement this directly. So what I'm gonna need, well, first of all, I'm gonna need source, destination, spare, and size, right? So I'm gonna say, well, let's not use size, let's use disk. So const disk is gonna be a const. I'm not gonna use dest and spare. I'm gonna use src. I'm gonna use, because these are more standard and short, dst, and I'm gonna use augs auxiliary for spare, abcd. I might not even need augs, but we'll see. Okay, and now what I'm gonna need is I'm gonna need the function move, which is gonna be a label move, right? And once we're done with the move, we're gonna want to ret. I don't have a specific ret instruction, so instead all I do is I just move from IAR to, actually from stack to IAR, right? So I pop my, what's it called? Function return address or something. Manually, that's gonna be our function. And now what the function needs to do is, let's see, if disk number is 0, then move disk to destination. So let's implement this. I need a jump. We're gonna be comparing to 0. Immediate to jump. We're gonna be jumping over this, so I need to jump to else. So I need not equals to 0, right? So if disk is not equal to 0, then I jump to else. It's gonna be a label else. Otherwise, so if we're not equal to 0, if we are in fact 0, what I'm gonna do is I'm gonna be moving disk from source to destination, and that's pretty simple. I just tell the magnet to go to source, which is mov src to IO, right? Then I need to toggle. Actually, yeah, I need to toggle. What was toggle? Toggle was 5, right? Toggle is 5. No problem. Let's say const toggle 5. What I'm gonna do is I'm gonna save toggle, because toggle is a constant and not a register. Save toggle. Oh no, my PC is broken. Be right back. So we're gonna save toggle to IO as well, right? So now we lift the disk, then we move it to destination. So destination to IO. And then we save, again, we toggle it. So toggle to IO. So this is the move inside the if. It's not actually, strictly speaking, it's not necessary to implement this if this way. Like, this move is the same as this one in the middle. So instead of just saying that at 0 I move the disk, I could say that at 0 I don't do any sub moves, or I could say that a 0 size move is nothing. So I could avoid this, but that saves on code, but that doesn't save on speed or function calls or anything else. So it only saves code, I believe. So let's not do that. Okay, so now we're in the else. This is going to be the more interesting part. So I will need, first of all, I'll need 2 calls to move. We have a fancy call now, which is immediately conditional. But what I want to do, I think, so call is effectively the same as jump, except it tells that we are in fact calling. So I can pass it a condition. So for example, call if equal, AB. But right now, I'm just calling unconditionally, so I'm gonna add const u call, immediate 1, immediate 2 call, right? Which will allow me to say unconditional call, underscore, underscore, move, right? So I call myself again. That's one thing, and then I will need to do this again. So you call, move, right? And in between these, I'm not gonna worry about the arguments for now. And in between them, I want to do this exact same thing, right? I want to do the move of my largest disk, right? So once I call this move, that's the equivalent of moving the top 3 or top 4 disks. Then this moves my largest disk, and then this will move my, again, my smaller tower to where it needs to be. So that's about it. And now comes the more interesting part. Now I need to handle local variables. So the first thing I did, initially, we call move. Actually, I never loaded the inputs. Let's load the inputs. So first we get, I believe I put them in order. So disk, first we get disk. No, IO, we load it to disk. Then we load IO to SRC. Then we load IO to DST. And then we load IO to auxiliary. So these are my inputs, and initially I call my move with an environment in which disk, SRC, DST, and aux are the initial values. But now, in order to make subcalls, I will need different source and destination, right? Because right here, if my source and destination are from here to here, I first need to put the smaller tower on aux. Then I move this, and then I need to move from aux to destination, right? So I need to mutate these values. I need to mutate aux and destination, and I also need to decrease my size. So, but then I pop from the function, and I need to get them back. So the game actually gives us a tip: push register values to the stack to save them before calling a function that changes them. And that's, I mean, that's pretty simple. I can do that pretty easily. So I save, basically what I do is I save my current state. I say mov disk to stack. I say mov SRC to stack. Let's just save everything for now. DST to stack. And I say mov aux to stack, right? I saved everything. Then I'm gonna mutate them, right? So I'm gonna say, I was at env1 here. I'm gonna do env equals, env2 here. I'm gonna call my move. It's gonna be called with move with env2 because I changed my env. But then once I pop, I need my original environment back. So what I'm gonna do is I'm gonna do that, but in reverse. So mov stack to aux, right? I pushed aux last. Now I pop it first, and so on and so forth. Right, source. Oh, would have been easier to just type out. So DST, SRC, and mov stack disk. Right, that's what I do. I think. There might be a better way, I'm not sure. I'm gonna have to think about that at some point, but for now, let's just implement it the naive way. Right, and over here, what I need to do is I need to mutate my environment. Which is also going to be fairly simple. I just need, first of all, I need to subtract 1 from my disk. So immediate to sub disk 1 save to disk, right? This is disk minus minus. Now source remains unchanged, but destination needs to become spare. and spare needs to become destination. So I need a flip, which means I'm gonna need a const tmp, abcdp. Right, so I'm gonna do mov whatever aux to tmp, mov destination needs to become aux, and then aux needs to become destination, or vice versa. So tmp will be my new destination. So aux becomes tmp becomes destination, destination becomes aux. So that's that. Yeah, and this is the first call, and the second call, destination remains unchanged, right? So my destination is as it was here. It remains unchanged. So now I need to flip. Yeah, actually, yeah, first of all, I need everything else for the move. All of this I'm gonna want. I'm also decreasing the size, the number of my disks. But instead of flipping source, instead of flipping aux and DST, I'm gonna be flipping source and DST. So DST becomes source. Is it? No, it's source and aux, sorry. So let's just try this. Aux becomes source. Yes. And source becomes this is for some reason this is very confusing in assembly. I don't know. I think it's right. Aux to TMP to SRC. Yeah. So we get spare here, and SRC to aux. We get source here. Yeah, that's correct. And I think that should actually be it. We don't need to call this function. We just fall into it, because assembly. Oh, you know what I missed? Yeah, I jump to else, but I will also fall through the else. So right here, I also need a ret. Right, once I'm done, I don't want to go into the else. So let's also add a ret here. So something like this should actually work. This is very much inefficient. I'm gonna improve this a bit. But let's first see if this works. Yeah. This looks ridiculously slow, but it does work, I believe. Yeah, it's very slow. Look at it. It takes so long. So the depth of recursion here is pretty high. We go pretty deep in. Like, in order to move disk 4, we need 2 calls to 3. Then we need 2 calls to 2 for each. So we need 4 calls to 2. We need 8 calls to 1. And we'll need 16 calls to 0. Right, so that's huge. So all in all, the sum of this is gonna be 2 to the 4th, I think, or 2 to the 5th. 2 to the 5th probably -1 or something like that. Yeah, so this is evidently pretty slow, but if we just let it run, yeah, success. But let's first improve this a bit. So first of all, immediately what I'm thinking is I'm only swapping aux and DST here, and source remains unchanged. So I don't need to push source to stack, and I don't need to pop it later. Right, so that's already 2 instructions saved. Same thing here, it's aux and source, and not destination, so I don't need to push DST to stack, and I don't need to pop it from stack either. So that's also good, right? Should already be a slight improvement. But that's not all, actually. I think this could be improved further. At least when it comes to the disks. See, the value of the disk does not matter to anything other than the calls. So I think it's safe for me not to save the disk here and not to pop it, right? And I can just, when I start my function, I can basically put it, well, let's first put it in the else, but I'm gonna think about it for a bit. So I can basically just decrement the disk. I don't need to decrement it again, but I don't need to save it either, right? And then down here, I can just increment it back. Oops. Down here, I can just do immediate to add disk 1 disk, right? So decrement, then I do 2 calls, then increment. Because I want it back when I'm popping. I think. Do I even? Wait, do I even? Yeah, I do, because once I call this, I want the disk to be the same for this one. Yeah. Okay, so that's already a bit of an improvement. Let's see if this helps. Well, rather, if this works, it definitely must help. Yeah, so alternatively, I could, of course, save the disk here. I could say move disk to stack, and I could pop it here. But that's actually one more instruction than doing +1 and then -1, or rather -1 and then +1. So this is already looking a bit more efficient, but I'm not entirely happy with these calls. The fact that I have to save before the call and pop after the call is a bit weird to me. Could I... So, an idea is, and it's actually kind of implied by this tip, instead of doing the save and the load for each call, could I attempt something like save at the start of the function, right? So save env to stack, then do stuff with env, right? Mutate env, and then pop stack to env at the end. That would save me these multiple things, but it doesn't actually seem possible, right? Because I need to... Yeah, I need to mutate my arguments before I call the function, because I need different ways to call the function. I need the function called with different parameters, with different arguments. Yeah. So I don't think that's possible. I'll give this a bit more thought. And then I'll be back with some more interesting stuff. Okay, one other idea. I don't like how these swaps are happening. Because there's only 3 pegs, once I know 2 pegs, the third one can be inferred from them, right? So for example, if I know that my source peg is 0 and my destination peg is 1, then I know that the auxiliary pin must be 2, right? And this is actually a pretty simple arithmetic operation. Because I know that the sum of all pegs is going to be 3, right? 0 plus 1 plus 2. This means that 3 minus the 2 pegs I have, so 3, for example, minus 1 minus 0, is going to give me the other peg. And this means that I wouldn't need to keep track of all 3. I would only need to keep track of 2, right? So source and destination. And that can save me, I believe this should be able to save me some instructions here. And instead I can front load my work to the start of the function. So let's try this. Let's copy this solution in case I want to compare them. So this is going to be, I don't know, it's still recursive, but it's 2 argument. Recursive lm rec doesn't fit reg to arg lml. So what I'm gonna do, we're gonna say that source and destination are things I save, and I'm gonna infer aux. And the way I'm gonna do that is I'm gonna do immediate one sub from 3 src to aux, and then immediate one sub from 3 dst. Actually, not immediate one anymore. Sub from aux dst, right? So this is essentially stating aux equals 3 minus src minus dst. Like so. Yeah, this is written to aux. So I can infer aux from src and dst now, and I cannot worry about it at all. Which means I no longer need to move dst to aux. Right? I don't care about aux. I no longer need to save aux. And this can be reduced to just aux to dst. Yeah. Oh, this is nice. Yeah, I think this saves me a bunch of instructions. And the same should be applicable here. Don't care about aux, so I only change src. I don't care about aux. Src to aux doesn't matter, but aux to src does. Oh yes. This is both much shorter and much more efficient, I'm pretty sure. Let's see. Unless it's broken. Oh no, it breaks. Why? Why does it break? Move aux to dst. This is frankly unexpected. Is my calculation for what aux is incorrect? So 3 minus src into aux, and then aux minus dst. No, this should be right. I don't need this anymore. That doesn't matter. Huh. What's up? So, what's gonna be the first, actually? Okay, I moved to 0, I moved to 1. No, but I think that's correct, is it? Oh, but then it picks up 1. What? Okay, let me debug this. Right. Aux got mutated. So, once I did this, it's fine, but then when we call this, it's gonna mutate aux, but it doesn't reset aux. So, I kind of do need to save it. So I could either reset it again before the next call, or I could just save what I got. Right, so move aux to stack, and then pop. Right, so else. Ooh, I will need to pop twice. Right, I will need to pop. Well, that's kind of fine. This is an interesting mix between pushing outside the call and pushing inside the call. It's weird. It's weird how that happens. Huh. Yeah, well, I mean, I guess. Yeah, the aux. Wait, no, that's not right. Wait a minute. So, okay, no, this is, wait. I'm not doing that yet. Here's the thing. the problem is not inside the next call, because aux got mutated. Next call will reset it to itself, and it will be correct. The problem is with this. The problem is with my new value of src. So src needs to be aux. Could I instead use a different formula for src? Well, could just do this. Right? Would that work? So that'll just add one instruction. Let's check. So src equals 3 minus src minus dst. Right, src minus dst into src. And this I don't need anymore. Right? And this is still fine, I think. Let's check. Okay, this looks to be working. Yeah. Alright, that's an improvement. It's kind of weird that this is this way and this is this way. Let me think about it for a moment. Well, you know what? I think I should be able to completely get rid of aux. And I should be able to get rid of aux entirely. Like, I don't even need to have aux as a constant. I don't even need aux as a variable. Instead, what I can do is I can do the same thing here. I can do, oh, come on. I can do immediate 1 sub 3 dst dst. And immediate 1 sub 3, well, let's do this consistently, so src dst. Actually, no, dst, src, dst. Yeah, so this essentially switches dst to the other pin that's not used. And it's still cheaper, because those two instructions would always be performed anyways. And so instead of now performing those two plus a move from aux to dst, I can just immediately do this on dst. So that's cool. Except everyone died. Be right back. Ah, we have a lost immediate 1 here. Let's see if this works now. It does. Great. Okay, this I'm pretty happy with. This is alright. 100 bytes. That's decent. I think that's decent. Only 3 registers, which is good. Yeah. Yeah, I'm pretty happy with this. However, this is child's play. This is absolute child's play. In fact, what's the score on this? 4.5K. Let me just show you the ASIC I was able to come up with. We have a gate score of 153. And let's see what we get as our final score. 333 versus 4.5K. And this does a thing every move. Every tick, something happens. So, no time wasted. Well, of course, I would expect that to be a general property of ASICs. They wouldn't need to waste much time for thinking. So, yeah, this is a thing. And in fact, I'm not sure, but I haven't seen this anywhere else on the internet. I have researched this problem a bunch. And so far as I can tell, this is pretty much my own completely unique solution to the Tower of Hanoi. It is inspired by some other stuff, but yeah, I would be very interested if anyone could link me to something that does this. Now, by this, of course, I don't mean the circuit. Obviously, pretty much any circuit I make is going to be unique just because the wires are going to be slightly different. I mean the actual idea of it and the algorithm this implements. And in order to understand this algorithm, I think I'm gonna go back to the whiteboard, the blackboard, the whiteboard. The board is black. So here we have our Tower of Hanoi. And first of all, I propose another simplification to this. Instead of having the pegs ordered in this way so that this guy is not really on the left of this guy, even though we can apply modular arithmetic as is intuitive for the Tower of Hanoi, I propose this kind of setup. So each peg is actually adjacent to each other peg, right? So we have this one on the plus direction of this one, we have this one on the plus direction and this one on the plus direction, right? So kind of clockwise is a plus direction, and then this one is counterclockwise, minus direction, minus direction, minus direction, right? And again, just like before, I suggest we don't think about where we're moving the tower. All that matters is that we have a source peg and we want the tower to not be on the source peg. Now, like I already explained, there exists a unique sequence of steps that gets us to the solution in an efficient manner. Now, of course, it's possible to do stuff like going back and forth, back and forth, back and forth, and getting nowhere. But if we want to solve the problem in the most efficient amount of steps possible, there is only one sequence of moves, and that is remove this, move it somewhere, move this, and then move this back, right? And that defines the recursive solution. And since this is the case, then necessarily any other solution will also be tracing the same steps as the recursive solution. My solution, this thing, the ASIC, is not recursive. This is definitely not recursive. There is nothing like recursion happening here. This is a closed form solution, and it's pretty much blind. We do not preserve any state of the tower anywhere. All we take as inputs is we take the move number. We have a counter for the move number. And even that is not really an input. This is kind of a state, right? The rest is just determined on the move number. Now, in order to understand how this happens, we are going to need 3 separate facts about the sequence of moves, the necessarily unique sequence of moves that gets us to the solution. The first fact is this: move number n involves disk size count trailing zeros of n. Now, I'm not going to go into too much detail on this one. In fact, I don't intend to go into too much detail on the proofs of either of these facts. But for this one, there exists a brilliant, as they all are, 3 blue 1 brown video, and I'm going to link to that. Hopefully it pops up here, or you can look in the description. But just as a brief explanation of what this even means, count trailing zeros is a mathematical operation on a binary number. We can have a binary number like anything, and we look at it and we find how many zeros are at its end, right? So these are the trailing zeros of this number. And so right now we have 4. If our number was something like this, for example, then we would have 0 trailing zeros, or if we have 1 trailing zero, or we can have 2 trailing zeros, and so on. So, for example, if our move number is, say, 3, or let's say 4, so 4 is going to be this, the 4th move, we know, is going to involve count trailing zeros of 4. Is 1, disk size 1. So this disk on the 4th move will necessarily be moved. We don't know from where, we don't know where it is at that point. We don't know where it's going to be moved to, but all we know is that disk 1 is going to be involved. Again, I'm not going to prove this. You can go watch the 3 blue 1 brown video. I'm just gonna say that this has to do with the fact that it's moved. Disk number n is moved after the smaller tower above it is moved, right, like I explained. And the amount of time, the amount of moves it takes to move a tower of size n-1 is 2 to the power of n-1 minus 1. And that kind of corresponds to these bit patterns in binary. You know, powers of 2, bit patterns, all that. So this is the first fact. The second fact is this. It's a bit difficult to state tersely and precisely, but let me just explain. So we have 3 kinds of moves between these pegs. We have a kind of move that moves between these two without regard to the direction, so from here to here or vice versa. We just know that certain moves move between them, so either this way or this way, right? The same way, oops, keep back the 3. The same way we have the kind of move that moves, come on, that moves between these two, and we have the kind of move that moves between these two, right? So overall, that's 3 kinds of moves. And that's what I mean by AB, AC, BC, right? And it just so happens that the correct sequence of moves constantly iterates between all 3 of these possibilities. So the first move is going to be between this and this. Then the second move is going to be between this and this. The third move is going to be between these 2 things, right? And then we're going to wrap around and it's going to start over. It's also going to be between these 2. Then we're going to have between these 2 and then between these 2. And so we'll have these triples of the pairs of pegs between which the disk is getting moved. Now, again, I'm not going to provide the full proof of this. I believe, well, yeah, I'm pretty sure I'm very certain all the proofs of these facts will involve induction, and I'm not gonna go with formal explanations. But long story short, this has to do with the structure of the recursive algorithm and with how these source and dest pegs are manipulated in these calls. And it just so happens that they always, the moves that actually happened, so this move and this move, right? The moves that actually exist in the real world happen to be called at times such that source, spare, and dest are juggled around in that order. So if, for example, if we take a look at depth 1, right? Imagine we call the move with depth 1 and source dest, right? What we're gonna have, we're not gonna be in the if, so we're gonna be in here. Now we're gonna call this move with depth 0 now, and source spare. So this is gonna get into 0 and an actual move is gonna happen. So we're gonna have a move between source and spare in some direction, doesn't matter. But, well, I mean, we know now, but by the time we reach depth 1, these source and spare can be mangled, right? Because we substitute spare for source and we substitute everything for everything at some point. So again, we're gonna have source and spare move, then we're gonna have source dest move, and then we're gonna have spare dest move. And notice how these are all 3 possibilities. These are all 3 pairs. This is not the full picture, of course, because we don't just have depth 1 and other moves happen at different depths, but I'm not gonna go into the detail of this. Hopefully it gives you an idea and you can work it out if you're interested. So that's the second fact, right? Knowing the move number, actually, when we have move mod 3, right, because these are triples and they repeat every time, we will know the pair of pegs between which the move happens, right? So by move number 3, we can determine AB, AC, or BC. So that's the second fact. And the final third fact, all even-sized disks always move in one direction. So for example, disk 0 will always move in a positive direction. So here, then it'll move here, then it'll move here. It'll move here, 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 right? Then we have an odd sized disk, and all the odd sized disks will move in the other direction, in the non-even direction. So in our example, this is going to be the negative direction. They're going to be going this way, counterclockwise. 1, 1, here, here, here. And this is true of them all. This is true of all the sizes. So for example, size 4, even, so it's going to be moving in this direction. So now every time we know that we're moving disk 4, we know that it'll be moving to the peg 1 to its right or left, to its positive or negative direction, depending on what even-sized or odd-sized direction is. This is also related, the proof of this is also going to follow from the form of the recursive algorithm. And this has to do with the fact that direction flips every time a call is made. So say we are in this call, direction from source to destination. So over here, this is going to be useful. It's going to be important to say that this is source. Say, for example, this is destination, and this is going to be spare, right? We have our call to source to destination is going to have a positive move in it, right? Plus source to destination. But then we're going to have, and it doesn't matter whether it's in the if or it's in the else. They're both source to dest, so positive direction. But now the next call down is going to be source spare or spare dest, right? If we take a look, source to spare is negative direction, and spare dest is also negative direction. So every time the direction in which we travel flips. Now, again, the meaning of source, spare, and dest changes when we get deeper into the algorithm, but this kind of pattern does work. It's still preserved because it doesn't depend on anything. And this also combines with fact number 1, right? Because we know that the moving of disk number n is happening on depth n, and with depth, with increasing the depth by 1, the oddity or evenness of the disk number, the disk size flips as well. So every time we flip the disk oddity, I don't know, evenness, disk mod 2, what's the word in English? Parity, I looked it up. With every depth, the parity of disk size is going to flip, and the direction in which this disk moves is also going to flip. So we know that parity corresponds to the direction. Now that we have these 3 facts, we can actually devise a full closed formula for how to solve the tower without looking, pretty much. So, how do we get an actual algorithm from these 3? What do we do? First of all, we're going to be taking track or keeping track of the move number. We're going to start counting at 1, and then we're going to increment every time we move a disk. Move number n is what was meant. Hopefully that was clear already. I didn't actually mention it, I know. We're keeping track of the move number. Now, every time, every move, we're going to be able to apply all these 3 facts. Let's see. First of all, we're going to apply fact number 1. Move number n involves disk size count trailing 0 of n. So, for example, if we're currently at move 4, the count trailing zeros is going to be of this. So count trailing zeros is 2, right? Therefore, the disk we are moving, we know that we are moving disk number 2. As of yet, we do not know where disk number 2 is. No idea. or where it needs to move, neither in relative nor in absolute directions. All we know at this point is that we are moving disk 2. Then we can apply fact number 2. From the remainder of 4, mod 3, which is 1, we can determine the pair of pegs between which our disk number 2 is going to move. So in this case, it's going to be, what's 1? It's actually not entirely set, but let's say it's these two. Now, still, we don't know which one of these disk 2 is on. We just know that it's somewhere here and it will need to be moved between them. However, we still have the third fact, and this says that all even-sized disks move in one direction. We know that our disk 2 is even-sized, right? 2 is even. Therefore, we know that it has a set direction. Now, which direction we move it doesn't actually matter as long as it's set. So at the start of the algorithm, we just choose a direction, for example, +1, so let's say right, and we'll have an even direction which moves this way. So if our even direction is this, then we have just established that, well, we need to move between these, and we need to move in this direction. Therefore, we know that we are moving from this one and to this one. So that's the move. We don't even need to know the size of the disk, really. All we need the size for is to know whether it's even or odd to know this direction. Right? So this is the algorithm. We can just repeat this every move. We can determine the pair of pegs and determine the direction, and then we move. And that's it. Now, before we can get to the actual circuit, we actually need to desimplify this first. You may recall that at the outset, I decided to simplify this task, to simplify this problem in two ways. First of all, we're not considering an ordered set of pegs like this. We're just considering some 3 pegs, which are not ordered. And second of all, I'm not concerned with where to move the tower. I was concerned with just removing the tower from its original peg. But that, unfortunately, is not the problem statement as is required from us, right? As is required of us. If we take a look, what we need to do, well, yeah, I'm not sure where it says that, but basically we need to move the peg, we need to move the tower from a source to a destination, where source and destination are actual concrete pegs. So for example, we might have to move this tower from this peg to, say, this peg. And this is a more complicated issue. This is a more complicated problem than what I have just described. Thankfully, though, these two problems are fairly similar and can be derived from each other. Or rather, the solutions to either can be derived from each other. So, when we consider this algorithm for this actual thing, let's first start with a basic task. Let's first make these pegs ordered again. So we're gonna have peg number 0, peg number 1, and peg number 2. But let's still consider that the tower is starting out on the 0th peg. And let's still try applying this algorithm. What we're gonna find out is whichever direction we choose, the towers with base disk even are going to move in even direction. So let's just set our even direction as left. Even is left, it doesn't matter. But let's say even is left. Which means disk number 4 by our algorithm will be moved left. And we know that disk number 4 only needs to be moved once. So it will be moved left, aka to 2. Which means the entire tower is going to end up here, right? However, if we had our tower an odd size, so not based on, or an even size and based on an odd disk, we would actually be moving disk 3 to the right, because it's not even, of course, and we would end up here. So this is the first challenge we encounter. We realize that our algorithm moves the tower to different pegs, depending on where the tower, or depending on the size of the tower. So it moves left if it's odd-sized, and it moves right if it's even-sized. This is the first thing. Now, the second thing is, we have so far assumed that the tower starts out on peg number 0, but that is not necessarily the case. At some points, the tower might start at peg 1 or at peg 2. And this is another challenge we're going to have to face. But thankfully, our algorithm generalizes to any solution just by reordering, air quotes, pegs. So, you know, if we know an algorithm that solves a problem where we move from 0 to 2, and we actually need to move from 1 to 2, we can just say that 1 is 0, 0 is 1, and then apply our algorithm as normal, right? And it would work just because it's, I don't know, it doesn't matter. There must be, I can't be bothered coming up with a strict statement of this, but hopefully this is clear. So yeah, we will be able to apply that. Okay, now, finally, but not yet finally, I can show the actual circuit, but finally I can show a Python script that implements the algorithm I just described. This is just the blind step function. The rest doesn't matter. This is a closed form of the blind step function, or rather, you know, an arithmetic form, and this is just a library, basically. I need count trailing zeros. But yeah, this implements what I just described exactly. First of all, we determine the disk number by counting trailing zeros of move. Then what we're going to do is we're going to determine direction from the disk, which is based on the parity of the disk. Next up, we're going to determine the pair of pegs. And here, again, this algorithm assumes, right now, what you're looking at, assumes that we are moving from 0, and it is the one that constantly moves even disks to the left. So this is an implementation that starts at 0 and moves even disks to the left. And that's hard-coded into these numbers. So on the first move, we're going to be moving from 0, from peg 0 to peg 1, and so on and so forth. The important part is these are all in the direction, they are ordered, and they are ordered in direction right. Right, so 0 to 1 is right. 2 to 0 is right. And 1 to 2 is also right. So at the point when we determine the pair of pegs between which we are going to move, we just return them as if they were, as if we were moving between them in the direction right. However, we know that our direction might not be right, it might be left. So if the direction is in fact left, we just take this pair and we flip it, right? So pegs is the reversed tuple of pegs. Yeah, that's the implementation of this algorithm for this tower. Now we're finally ready to take a look at the circuit. Don't be scared, and also don't be alarmed that this is different to what I just showed. While I was thinking of the explanation, I improved this a little bit, but this is still the same. Let's start with the clock. This thing right here, you've already seen it. This is just a pretty regular, basic application-specific clock. It has two phases. So the first phase is going to be the initialization phase, where I will load in my values. And the second phase is going to be the actual solution phase, which is a single loop, which does, it moves, let's take a look. So we move the magnet to where we need to pick up the disk, so from, then we lift, then we move the disk to where we need to drop it, so to, and then we drop it, right? And then rinse and repeat from lift to drop, from lift to drop, from lift to drop, so on and so forth. This is just gonna be our loop forever. Now, let's first talk about the initialization phase. I load everything. I load size, I load source, destination, auxiliary. And this is very important. I load them into registers. And in order to then output a value saved from a register, I just need to power one of these pins. So if I want to output source, if I want to move my magnet to source, I just power this pin. If I want to move my magnet to destination, I power this one, or auxiliary, this one. And this is very important because this abstracts away the actual numbers that are source, destination, and auxiliary. Remember how I complained that my algorithm assumes I start out at 0? Well, this completely solves it. Because I can still apply my algorithm. It will tell me the numbers between I need to move. So for example, I need to move between, say, from 0 to 2, right? But these 0 and 2 will just immediately translate into this pin. This is the 0th pin, say, and this pin, the 2nd pin. So I will have source to auxiliary, even though I don't actually know which numbers they are. I don't care which numbers they are. All I need to know is that they are saved into these registers. So this is the first important part. Next up, after the initialization phase, we have our loop. And what happens in the loop is, first of all, we need to keep track of the move number. The way that's done is these two things here. Let's first take a look at the counter. This is a custom counter. It's custom for two reasons. First of all, it's just reduced because we don't need numbers as large as 255. We don't go that far. But more importantly, this counter only counts up when it's powered. So it has this input. I cannot overwrite it. It will always either count up or remain the same, but it will only count when powered. And this is important because my loop only needs one increment for the move, right? Because this is a single move. From lift to drop is a single move, but it's multiple ticks because I need to perform multiple things. So I only need to power my counter. I only need to increment. When I start this loop, we start counting at 1. And when the loop restarts, next move, we increment the counter. And that's what happens. So we can take a look. 1, then increment, 2, increment, 3, and so on and so forth. So this is the actual number. This will keep track of the actual full move number. But the only reason we actually need it is, if we take a look at the Python here, the move number is only needed to determine the disk. And actually, the disk is only needed to determine direction. So really, all I need the move number for is I need count trailing zeros mod 2, right? And this is what this is. Count trailing zeros mod 2. Actually, let me optimize this slightly. Haha, done. I just reduced it so it's only 6 bits as well, because again, I don't need large numbers here. I guess we can take a look in here real quick. This might be familiar. This is based on the comparison operator right here. And the comparison operator works by starting at the least significant digit, compares them until it finds different digits. That's very similar to the algorithm of trying to count trailing zeros, right? We need to start from the least significant digit, and we need to continue until we find a 1. So that's what this does, effectively. However, like I said, I only needed mod 2. So I don't actually need all the values from 0 to 8. I only need to know whether they're even or odd, and that's what these are. I just have a 1-bit output. And yeah, you know, if I get count trailing zeros equals 2, then I don't need to output anything, it's 0. If I get it equal to 5, for example, I will have an AND active somewhere, and it will be a 1. So that's this. Now, you might be wondering, I still need this part, match move mod 3. And I could have it in here. I could plop, say, a div mod for 596 gates. I could plop a div mod and divide this number by 3. But that is, of course, prohibitively expensive. I could also implement a specialized mod 3 component, but that is still very expensive. And so instead, what I use is a solution I'm actually quite pleased with. It's this thing. This thing is an analog base 3 counter. I guess it's best explained with a demonstration. So we start at 1, then loop 2, then loop 3, loop 4. Well, 4 wraps over to 1, and so on and so forth. It's quite simple, really. All this is just, I mean, it doesn't look that simple, but it's just because there's 3 lines here, there's 3 lanes. But we have a triple mux, and normally, if we are not counting, so if this is off, normally this loop just remains constant. Otherwise, if we are counting, then this thing just, you know, rearranges the 3 wires. So I have 3 wires running, and I need this one to go down, I need this one to go down, and I need this one to go up. And that's exactly what we have up here, right? It just ticks forward. Now, this part is a bit weird. This is necessary in order to kickstart it, because obviously it starts out completely zeroed, and that's no good. We're gonna remain completely zeroed. So what this does is the first time it receives an input, it's gonna override the first thing, the first bit, with a 1. So that's what happens. Once we're told to count, we count to 1. So there we have our analog mod 3 counter. And the important part is it's completely synced with the full counter, right? And so long as they are synced, I don't actually need to get move mod 3, because move mod 3 is just represented by this. So that's that. Next up, I guess this part. So this here entire thing pretty much encodes source, destination, and auxiliary in analog, just like here. Now, for the moment, let's try to disregard these flips. Let's just connect it like so. Now, if we take a look here, this is pretty much a mux. It has 2 3-bit inputs. It has 2 3-bit, or it has 1 3-bit output. Except it's a mux that's not always on. It's more of a selector. When I need a from, I will select a from. When I need a to, I will select a to. And this output, the three wires that are the output, correspond to my source, destination, and auxiliary, or in, you know, number terms, they are 0, 1, and 2. So this is 0, this is 1, and this is 2 for my algorithm. So what this does is pretty much this right here. Now, at this point, we have our decoder board set in the same way that this is. This will return the from and the to in an order such that a move between them will be right. So, you know, the thing I explained, 0 to 1 is right, 2 to 0 is right, 1 to 2 is right. So here, if we take a look, for example, this is move mod 3 equals 1. So we will have our from being 0. So from equals 0. And then 2 will be equal to 1. Right? This is a 1. So 0, 1. Same thing goes for the 2, same thing goes for the 3. However, without those flips, what this does is just that. This just sets the pegs in the right direction. Now, when I introduce flip back into the mix, give me, I think this is a base thing now. Yeah, flip here and here. Actually, let's just start with this one. What this does is this literally encodes this line of code. If we have our direction that is not right, that is left, then we need this tuple to be reversed. We need to move not from source to destination, but rather from destination to source, right? Well, not from A to B, but rather from B to A. And this is what this does. It just flips the from and the to inputs and outputs them. This is, I guess I should try to show this off real quick. Give me an on. So normally, it just lets all signals through, normally. But if we enable it, it flips them, right? So bottom goes to top and top goes to bottom. Right, like so. That's all. It flips these two inputs. So at this point, we already have our algorithm completely implemented, and this will actually work. This will actually solve all the problems if we run it. Success. So why the final flip? Why this flip here? Well, the reason for this is the fact that the algorithm as implemented is a little bit inefficient. Like I said, like I explained, it moves even towers left, and it moves odd towers right. Odd based and even based, I mean. That is not always what's required of us. Sometimes we need to move the tower in a different direction to what its parity dictates. For example, so I think the 4... Yeah, the 4 is fine, but if we take a look at the 3, so let's run the 4. Yeah, so right here, let's take a look at this 3. The algorithm is going to solve it, but what's going to happen first is it's going to move this 3 to the 1, and it's going to completely rebuild the tower here, right? But what was actually asked of us is we needed to move 3 not to the right, we needed to move it to the left. We needed to move it to 2. And this algorithm will work, it will proceed, it will continue, and it will eventually put the 4 onto there, and it's fine. But that's not what we want. This is wasteful, right? This is a wasteful solution. This wastes a lot of moves. So what I do right here is I do another substitution, another flip. And this one is a flip between destination and aux pins. Now, what this means, the source pin remains unchanged, the source pin is set. But if we know that the algorithm moves the tower to this, let's say this is aux and this is DST, right? If we know that the algorithm actually moves the tower to aux while it needed to move it to DST, just substituting, just calling this aux and that DST will put us in the right position, right? It'll put us where we want to be. I hope this is making some sense. So yeah, that's what happens, and it is based on the parity. So let's trace this. We have size going down here, and the parity, so the first bit, gets saved over here. This is just basically a very simple 1-bit write-only piece of memory, which just sets once at the first tick and stays the same. So if we are odd, then we know that the algorithm is moving us in the wrong direction and we want to move in the right direction. And we flip directions of movement. Okay, that's it. I guess the toggle this is just for prettiness. This is a constant. It's kind of like a register, except it encodes the constant 5. So that's all. Yeah, now I think I have explained everything. This has actually been very difficult to explain, and I have spent an ungodly amount of time, frankly, on this problem. Just because I didn't feel like the basic recursive solution would be interesting enough for a video, and besides, I do like my ASICs now. I might even consider recording a special separate unlisted video with a huge rant about a lot of things I encountered along the way. This turned out to be a very, I don't want to say difficult, but a very annoying and a very deep problem. There's a lot of symmetries and asymmetries to this. There's a lot of interesting facts about it, which I could discuss for a long time. But yeah, this will be it for this video. Sorry if the explanations were not clear. I tried my best. I have spent many hours re-recording these. I know they aren't perfect in the end, but I can't spend any more. And that'll be it for me. Let's take a look at our final score, actually. 299. I optimized it further with the reduction of these things. So sub 300 with a tick score of 128, which is perfect, I think. Yeah, that's perfect. Yeah. 292. Wait, I thought it was 299. So here it's 299, and here it's 292. Okay, sure.